Hi everyone, welcome back to the Cardioid simulation series, an interactive journey into vector algebra. In this episode, we are going to explore the basics of vectors and understand how vector operations like addition, subtraction, and scaling work visually. Let's begin with the core idea. What is a vector? A vector is something that has both magnitude and direction. Here is a vector called P, shown in blue. It points up and to the right, and its length represents its magnitude. Here is another vector called S, shown in green. It points in the same direction as B, but it's shorter. S is called scaled down version of B. It has the same direction, but a smaller magnitude. Finally, here is a third vector called D in red. It points in a completely different direction and has its own unique magnitude. This clearly shows that vectors are fully defined by two things: a magnitude, i.e. how big the vector is, and a direction, i.e. where the vector is pointing. And both of these are so essential to understand how vectors work. Now, let's look at vector components. Every vector can be broken down into its x and y components in case of 2D. For example, if a vector has components 4, 4, it means it goes 4 units in the x direction and 4 units in the y direction. When we decompose the vector, we can see these individual movements clearly. This is very useful when we need to add or subtract vectors later on. Let's now see how vector addition works. We have a red vector called A at point 2, 3 and a blue vector called B at point -3, 2. Now, to add these vectors using something called tip to tail method, we take vector B and move its tail to the tip of vector A. And the resultant vector shown in green is drawn from the origin to the tip of moved vector B. This green vector represents A plus B. And that's how vector addition works geometrically. You stack one vector onto the other, and the final vector connects the start to the end. Now let's talk about vector subtraction. We again have a vector called A at point 2, 3 and another vector called B at -3, 2. Now, to subtract vectors, first we invert vector B by multiplying it by -1. This turns vector B into -B. Then we move the tail of vector -B to the tip of vector A. Now, the resultant vector, shown in green, is a new vector from the origin to the tip of the vector -B. This green vector is A minus B. So, vector subtraction is really just adding the negative of a vector. It gives us the direction and distance from the tip of one vector to another. Now, let's see how vectors work in real life. Imagine you are applying different forces to a ball. We apply a small force, shown in blue. The ball moves up in a small parabolic arc and then falls down due to gravity. Next, we apply a slightly stronger force in the same direction, shown in red. This time, the ball travels higher and farther. The parabolic arc is bigger. Finally, we apply a smaller force directly to the right, shown in green. The ball shifts to the right and then falls. So what this shows is that the magnitude and direction of each force vector directly control how the ball moves. This is why vectors are essential in physics. They allow us to predict motion accurately. Let's now see vector addition in action. We apply two forces to the same object at the same time. One force pushes to the right and the other force pushes upward. When we add these two forces, the object moves in the direction of the resultant vector. This shows how vector addition is used to calculate the combined effect of multiple forces acting together. Now let's see vector subtraction in a real-world example. We have a bigger ball at 4, 3 in yellow and a smaller ball at 3, 0.5 in cyan. And the goal here is to find a direction of the force to move the smaller ball in cyan towards the bigger ball in yellow. And this is exactly where the vector subtraction comes into picture. We subtract the position vector of the cyan ball from the position vector of the yellow ball. This gives us a new vector, let's call it R, which points from the smaller ball toward the bigger ball. Normalize it to get the direction. Now that we have the direction of the force, we apply the force to the smaller ball and it starts moving toward the bigger ball, exactly what we wanted. That's all for today. If you found this helpful, please subscribe, like, and hit the bell icon so you don't miss the next video in the series. Thank you for watching and see you in the next episode.